So Michael Trottier from DuPont will talk about chlorine.
Good afternoon, everyone. My name is Michael Trottier. I'm actually a graduate from the University of Rhode Island in 1993, 92. I actually graduated from the chemical engineering discipline and recognize many of the professors here, in particular, Dr. Nicola and Dr. Gray, who I had as undergraduates, and I'm sure they're putting you through the same rigor that I went through. I can't even count how many years it is anymore. After a while, you just go and work day by day. But what I want to talk to you about today is chlorine dioxide. I don't know if you're familiar with it, but it's a chemical that's used in water disinfection, and it's primarily used as a substitute in many cases for chlorine or other more commonly known disinfectants. And what I like to do is kind of go over the chemistry of chlorine dioxide and some of the applications, and talk a little bit about nitrification, which Dr. Nicol wanted me to expand upon a little bit. But just to kind of give you a general sense in regards to the technology and how it's used, and really where some of the benefits are, and its uses over current traditional uses, in particular chlorine or, in that case, bleach. So just to, people think of DuPont, they think of a big company, and it is quite a big company, and it has a pretty wide spans globally. It is a North American-based company, primarily based in Wilmington, Delaware. But just a little bit of history of how how it's situated here in Rhode Island. About 60 years ago, there was a small company in North Kingstown called International Dioxide that actually was started by a bunch of dentists that were trying to essentially cure halitosis, and they kind of came across chlorine dioxide as a potential chemical use for this. And since that time, in these past 60 years, we've kind of grown from that initial application into much wider applications, industrial applications for that matter, particularly in drinking water or industrial applications, as in cooling towers or other processed water as well. We pretty much operated as a small business until about 1998, when we were bought by Engelhard, who owned us for about 3 years. And then subsequently in about 2000, DuPont had acquired us. In that time, I would say from 2000 to about 2004, we were just this small little business within DuPont, multi-billion-dollar company. Each platform at the time was probably, of the 6 platforms that DuPont had, each one was doing about $6 billion. And we were a little company maybe doing $5 to $6 million. So we were really small potatoes. In about 2005, the DuPont organization came and really looked at us and really challenged the organization to look at clean water. And DuPont made a very conscious effort to look at clean water technologies. And the IDI had a very interesting technology in regards to how to generate chlorine dioxide, particularly in the case of in a very safe method, which is really what, when you think of DuPont, I hope that's what you really think of as safety, because that is one of the major benefits of DuPont, and really what it likes to promote is safety. It's one of our major core values. So DuPont had us about 2005, and then since that time, we operated as a subsidiary, and then in 2008, we actually became all DuPont employees and have been operating as such. One of the advantages of the site that we still, in some cases, I'd like to say, is operate much like that small business that we were. Basically, every function that you can imagine in a business is located right up at Quonset Point. That includes engineering, sales, marketing, sourcing, really even accounts payable and receiving. The only thing that has been really integrated into DuPont has been our HR. So we have a little bit of the luxury. I wouldn't say it's a utopian company, but we have the luxury of operating very dynamically as a small business, but yet we have the corporate structure of a large company in DuPont. So that's a little bit of history. And as you go out into the field, you're going to get exposed to a lot of different types of companies. And personally speaking, most of my experience has been in small businesses. This is the first time I've ever worked in a large corporation before. And in this particular situation, one of the nice things about working in a small company is you have a direct result on the revenue and the health of the company itself. And there's no better feeling of that. I mean, you feel the pain both ways. When things are going wrong, you feel it, but when things are going well, you really feel it. And so that's one of the benefits that we have at this particular site. And there's a lot of energy. So just to talk about chlorine dioxide, I'm not sure how many of you are familiar. It was first used in 1944 in Niagara Falls in the United States. It was used throughout the world earlier, but at least here in the United States, it was first used in Niagara Falls. And at that time, it was used primarily for taste and odor. The big issue is, I don't know if anyone has hiked or taken a drink of water coming out of a stream, or and you kind of taste that earthy taste to it. This is what chlorine dioxide is really known for taking out, and was one of the original uses of the technology. Right now, there's over 500 installations throughout the United States. About 13% of the population uses it, and it continues to grow. The primary driver for using chlorine dioxide is strictly regulatory, and I'll go into the reasons of that a little bit later. But it has uses in Europe as well as in Asia as well. Just to kind of go over some of the basic chemistry of chlorine dioxide, when you see it, one of the things I really want to stress is that, and it's really one of the biggest hurdles that we have when we're trying to educate our potential customers or even folks like yourself, is that when they see chlorine, all of a sudden they start thinking about chlorine gas and bleach and these types of compounds. And although chlorine dioxide does have a chlorine component to it, it behaves very differently than those chemicals I just previously mentioned. It does have a very similar type of bleach kind of chlorine smell, and it does kind of affect you in a similar way in that it attacks the mucous membranes, kind of dries it up. It's that same type of acrid smell. But as far as its reactivity and what it does, it's actually very different. It is a gas. Typically, the way it is distributed is it's a soluble gas, and most times you will see it in the form. It's going to be it's sometimes dissolved in some type of matrix, typically water. Concentration ranges are anywhere from 3,000 and below. One of the big issues with chlorine dioxide is when you start getting into concentrations above 10%, you start getting into some really explosive situations. So having at this concentration is extremely safe, and part of the education that we do. One of the other advantages of chlorine dioxide is that once it's formed, it has its effectivity is quite large over a large pH range. Typically, from pH of 2 all the way up to 8, sometimes even 10 as well. If we start going up a little bit higher than that, you start getting some decomposition that occurs. Just for those that are familiar with chlorine, it is, as far as its Pell and Stell rating, it's basically one order of magnitude lower than that of chlorine. One of the nice things, and if I say attractiveness of the particular technology, is as soon as you smell it, you're already pretty much over the limit. And so in that particular case, you have a good sense of when you have a chlorine dioxide in the air. So when you look at chlorine dioxide, basically it's used for oxidation as well as disinfection. But when you look at the oxidation potential, you say I twist this somehow? There we go. If you see the list here, you can see we have a number of oxidants that are used in the industry. The ones that I've highlighted here in red are typically used for oxidation and disinfection. You see we have ozone, chlorine, chlorine dioxide, bromine are some common chemicals that are used for disinfection. And if you look at the list there, you see that, well, chlorine dioxide doesn't look to be all that great. When you look at it, ozone seems to be really, really nice, as well as chlorine. Well, they are very powerful oxidants, and many times they're used just for that reason. But we actually take advantage of one of the limitations that chlorine dioxide has is because it's somewhat selective in its reactivity, we're able to maintain a residual within a system, as well as it being a little bit more selective. So, as an example, in a power plant or a refinery or something, or an ammonia plant, if they have a process leak within their heat exchanger where they're getting ammonia that's going through their system, going through their cooling system, any of these other oxidants will react with that ammonia, essentially increasing their demand and their use of that particular oxidant. In the case of chlorine dioxide, it doesn't react with ammonia. So you still keep your biosolical activity, keep your dosage low. In the meantime, the plant is working through its issues with the process leak that it has. So we like to take advantage of the limitation that it has in regards to its oxidation. As far as chlorine dioxide chemistry, there are really 4 recognized ways to generate chlorine dioxide. Just to backtrack a little bit, one of the issues with chlorine dioxide itself is that it's a material that really can't be transported over the road. The DOT has put a limit of 3,000 parts per million as the maximum concentration that you can actually transport, and the reason being is strictly for safety. So it really becomes cost prohibitive to really ship in really large quantities when you need a large amount of disinfectant to ship chlorine dioxide. For small laboratory scales, or maybe even some pharmaceuticals or spot treatments, these type of concentrations are perfectly acceptable. But when you're looking at cooling towers or water plants where you're treating millions of gallons a day of water, this does not happen. So in order for you to essentially make chlorine dioxide, you have to have some generation technology, and essentially that's one of the components that the IDI group provides, is that we build these chlorine dioxide generators to essentially bring together two precursor chemicals, one being sodium chloride, which is the precursor that we provide, as well as other precursor that the customer will provide, which will either be chlorine gas, an acid, or bleaching acid. And there are also electrochemical methods as well that you can produce chlorine dioxide from chloride as well. As you can see from the reactions that are up here, the 2 preferred reactions that we like to use are the chlorine gas, as well as the acid bleach reaction. As you can see from there, there's pretty much a 1-to-1 relationship. For every mole of chloride, you're going to get an equivalent mole of chlorine dioxide. And then from there, you're just working on the efficiencies of the generation technology. So typically, we can get about 95% conversion of our chloride into chlorine dioxide. And some of these other competing technologies, where you start looking at the chloride acid, you can see that you're only getting, on a theoretical basis, about 80% conversion of the chloride to chlorine dioxide. There are some other issues in regards to this chemistry as well. What's particularly nice with the chloride, bleach acid, and chlorine gas, what's not really shown in these reactions, is that really the reaction is the formation of hypochlorous acid. That is actually what is reacting with the chloride to form the chlorine dioxide. And that reaction happens extremely fast, typically within less than 1 second, if not milliseconds. This particular acid chloride reaction occurs in the second minute time frame, and the issue that occurs there is that in order to preferentially form the chlorine dioxide, you have other competing side reactions that are occurring. So you're actually generating other chemistries inside the matrix as well. So you're not always getting this 80% conversion. But nonetheless, all 3 or all 4 of these technologies are available in the market and are used for a variety of degrees depending on what the customer needs are. Again, just a kind of a reiteration and a comparison of the 2. One of the things that really differentiates chlorine dioxide, in particular between chlorine, is the fact that chlorine dioxide is strictly an oxidation reaction. And that's very important, particularly when it comes to drinking water and the regulation of disinfection byproducts, PHMs and HAAs. In the case of chlorine, it can oxidize, but it can also substitute that chlorine, and that's where those regulated products come into play. In the case of chlorine dioxide, it's strictly an electron transfer, and there's no formation of these bad disinfection byproducts. And just another example of what happens. So basically what happens is, as with any type of electron transfer reaction, we spend all this time taking the chloride, bringing it to chlorine dioxide, bringing it to kind of its most energy stable state, and its reaction as it forms back to chloride. So there are some additional concerns in our technology that we need to be aware of. In that chloride, there's also a regulated material. So as we go through the analysis of a disinfection process or technology, We need to understand how much of that chlorine dioxide is being reacted and how much of the chlorate is coming back, and so that we're not being out of compliance itself. So just a kind of a summary in regards to the overview of chlorine dioxide in the differential case. I mean, it's a broad-spectrum biocide, and it's also a very selective oxidizer. And we utilize this selectivity in a lot of different applications. And at the end of the presentation, I can show you a number of applications and talk to you about them. So let's just go through some of the applications. The major driver in a lot of what we do is in potable water disinfection. And there are a number of methods that you can use for disinfection. One of the things that we like to promote with chlorine dioxide is that it's not necessarily a replacement technology for what you're currently using. In many cases, it's actually more of a synergistic technology, and it helps to either make what you have already better, or it helps to replace something else that, in addition to another problem that you may be becoming. It does minimize THMs and HAAs, as well as having your advantage of taste and odor as well as in color as well. And maintaining a residual is important. You want to know how much you put in there. So as we go through the, kind of the drivers, this just gives you, this is kind of a summary slide. So one of the things that water plants are particularly driving for is they need to have what's called CT credits, or contact time credits. Basically, the EPA has defined certain concentration and time thresholds for various organisms and that may or may not be within their water plant. And so in order to make sure that they get the effective log kill, that they have these CT credits that they need to maintain. Each one of these organisms, whatever they may be, Dysboridium, various E. coli, they have various log kills that you need to maintain. And the EPA has stated what those contact times are and the effective kill concentrations that you need. Iron and manganese. This is a particular problem here in the Northeast, but it's also and in the West as well. Iron and manganese are dissolved metals in the water, and they present a number of problems, not just so much in the water plant themselves, but also in our own household drinking water. In that first of all, the water comes out brown when you're looking at the iron. Chlorine dioxide is very good at essentially taking out iron and manganese out of the water. Basically, it will sequester the iron and or manganese. You go through another process where you basically will then just raise the pH and precipitate out the iron and manganese and then go on. This is usually employed at the beginning of a particular process plant. Taste and odor, as I mentioned before, that kind of gypsum, earthy type of smell is very good at taking out. THM, HAA reactions, as I mentioned, chlorine dioxide does not form these type of components. Improved finish turbidity. This is another water quality component that many water plants monitor at their water plants. Control of zebra mussels. I don't know, many of you may or may not be aware of various issues of these quagga mussels. Probably occurred maybe 15 years ago, where they started to see a number of the intake plants, particularly in the Great Lakes, where these quagga mussels were being seeded by large tanker ships that were coming over from Asia. They were in their bilge. Essentially, they were seeding into the Great Lakes, and intakes for treatment plants, any big water plant, refinery, the grates are like condos for them. It's a buffet. These organisms grow extremely fast, and chlorine dioxide is a really effective chemistry to keep quagga mussel control in these intakes. Once we have one particular water plant I can think of in the Finger Lakes up in upstate New York, and they do 2 treatments a year. And what they tell me is that when they do a treatment, particularly after the winter, the first time in the spring, the first thing they see are all the bodies that come through, and then the next thing are all the shells that come in, and it really plays havoc within their plant to get rid of these zebra mussels. Nitrification control. This is really more of a technology used for those that are using chloramines, and there's a lot of ammonia bacteria, ammonia-absorbing bacteria, and so the chlorine dioxide helps to to control that as well. And then there's wastewater disinfection, which is something that we're looking at as well. But you can see as we go through, just looking at how chlorine dioxide stacks up in regards to some of the other disinfectant that are out there. And you can see it's not necessarily the best, but it's not necessarily the worst. And one of the things that we like to promote again with chlorine dioxide is it hits that kind of that middle ground where we need to hit a lot of different technologies or a lot of different issues that you need to solve in your particular plant. Just some quick kind of overviews or rules of thumb in regards to how much iron in your plant, how much chlorine dioxide, to give you kind of a sense of the amount of chemistry that's required. Basically, it's almost 1-to-1 for iron and 2.5 to 1 for manganese. Taste and odor control, I kind of went through. One of the things I wanted to just kind of go over, as I mentioned before, chlorine dioxide is really it's more of a synergistic type of technology. And in particular, most water plants are battling THM and HAA reductions. They have very strict limits in regards to what their disinfection byproducts are, and they fight this all the time, particularly in the summer. And so there are a number of strategies that they have to employ, changing the chlorination, optimize sedimentation and filtration, use of chlorine dioxide. They may use GAC or membrane filtration, ozone, ultraviolet light. But my point in this particular slide is that, chlorine dioxide can help to solve some of the problems that they may have in using their, in solving the THM and HAA technologies. Nitrification, just to kind of go over, this is an area that's a little bit new for us, and we've been we actually just got a certification by the EPA to use chlorine dioxide / chloride for nitrification. And one of the big issues that occurs with, particularly with chloramine use, is that as the chloramine dissociates itself, we have these ammonia bacteria that are in the water, and so they start to consume the ammonia. They start to consume the chloramine, which is used as a disinfection. So with the act of adding the chlorine dioxide, we help to prevent these ammonia bacteria from forming and propagating within the system. And once you start having these organisms within the water, you get decreased alkalinity, the water tastes bad, you start getting lower disinfection, and then it just starts, really the whole ball just starts to go over and over again. Just as a summary, some of the techniques that are used are flushing, breaking chlorination. A lot of times they'll go on and off. They'll do cyclical chlorination to help minimize the formation, as well as do higher chlorine residuals. So as I mentioned, one of the reasons for using chlorine dioxide, it doesn't react with the ammonia, so now you have your chloramine in there for disinfection. It's effective at low dosages. This is, again, one of the big advantages of chlorine dioxide, particularly over some of the other oxidative chemistries. Because of its lower reactivity or oxidation potential, typically the dosage that's required in many applications is much less than that you would see in particular in chlorine. And a lot of it has to do with the fact that since chlorine dioxide is less reactive, or is selective as we like to say, it's really only going after the microbiological demand that's in the water. And so when it's not reacting with other things that you may have in the processed water. As an example, in a cooling tower, they don't just have, they'll have scaling inhibitors, and they'll have some other type of chemistries in there. Many times these other oxidatives, just by their nature, will react with these chemistries as well. And so that's nitrification control. Just some other industrial applications. I put this slide up because I had mentioned the quagga mussel, but it's somewhat the same. We have this algae growth. Again, chlorine dioxide, and for that matter, some of the chloride as well, is very good at dealing with this type of microbiological formation that occurs on intakes, on heat exchanger tubes, and a variety of other type of components, both in a microfouling as well as in macrofouling. And just an example, this is a chlorinator. They were actually using a bleach generator to essentially clean some tubes, and here you can see in this particular case, this really, all these tubes are all just clogged up and then just with 1 year in chlorine dioxide, they almost look brand new. One of the issues that we have many times, particularly when we go into a cooling tower application that has not been using chlorine dioxide, one of the concerns that we have is we typically have to go in very light initially, because chlorine dioxide is really good at attacking that biofilm, and we have to minimize the sloughing off of that biofilm, otherwise we'll just clog out that whole system. But once the film has been removed, just very low amounts of chlorine dioxide help to minimize and prevent the attachment of the organisms and the growth. And just an example of a cooling tower. This is an area that we've been looking at very recently, and we've been having a good amount of success with cooling towers itself. Just to kind of give you an overview in regards to applications, this is our kind of our, all of our areas that we can go after. And one of the big advantages in our particular industry we have is that there is no lack of opportunities for us to go after. Really the big issue that we have is we have to pick and choose and figure out which ones are the most important to us as well as to our customers as well. But I mean, if you look at some of these, all of these hit people in various ways. We have power utilities in regards to cooling, potable water, cooling tower, fruits and vegetables. We actually treat processed flume for waters for tomato canneries, ammonia plants, paper, pulp and paper, either used for bleaching or slimicide, hard surface sanitizers, RO plants in order to maintain minimize the biodemand on the filters themselves. I talked about zebra control, wastewater oxidation, odor abatement is another area at sewer lift stations. NOx oxidation, this is becoming again another air quality. Very good at essentially bringing the NO to NO2, which can be further scrubbed out. Another big area that's been happening is in oil and gas hydrofracturing. I'm sure you've heard a considerable amount of talk in the news with the tar sands that are up in Canada, as well as the Marcellus natural gas fields that are in Pennsylvania. As I was mentioning to Dr. Gray, in hydrofracking, I'm not sure if you're familiar with the technology, but basically what they're doing is they're just taking water, extremely high pressure, pumping it down into the ground, and they're just fracturing and essentially trying to release out the natural gas and the components in there. But there's a couple issues that occur when you do that. The first of all is they don't want to be putting down water that's essentially going to contaminate their well. That's one of the big issues they have. The other issue is historically what they have done is that they've taken the water from a local pond or resource, use that water to go downhole, and then the water just gets distributed out in the environment. There are now these small little businesses that are actually operating, calling themselves water reuse, that actually go to these frac sites, take the water that's being used at the frac site, and bring it to a treatment facility where they'll treat it, essentially guarantee that it's okay to go back downhole and getting back into this reuse and recycling. This is an area that is becoming particularly both here in the Northeast, or I should say in the Pennsylvania area, as well as in the Colorado. Rendering, odor control. I don't know if any of you have ever been to a rendering plant. Chlorine dioxide does a great job in killing the odors that are coming off those rendered fats. Very nice. Legionella control, wastewater disinfection. We also do some brewery and clean in place, and as well as even ethanol fermentation. Just to talk about this application in general, it's just to give you a sense of, when we're looking at different applications and trying to think out the box a little bit, in this ethanol application, one of the advantages that we're providing is we're essentially controlling the microbiological content inside in their fermenters. And historically what they have done in the past is they've used antibiotics. And the concern in particular in the ethanol arena is that when they use antibiotics is that these antibiotics then work their way throughout the food stream, and that potentially that we can ingest them as well. And so we provide an alternative to that, and it's been quite successful as we move forward. But again, just to kind of give you a sense, when you think of chlorine dioxide, or when you think of any technology that you may go into, try to open up your mind into looking at other applications and try to take what is the innate power or innate unique feature of that particular element and how can it be applied to solve other problems that are out there. And then you come up with this type of map. As I stated, our biggest issue that we have is we don't lack opportunities. There are plenty of them up here. Our issue right now is trying to pick and choose and make sure that we have a good business plan. Just a kind of a quick summary in regards to chlorine dioxide itself. I've talked a lot about the positives, so I think I don't need to go over onto that side. But what I'll do is I will talk about a little bit of the negatives in the end. So there is a cost component to this. I think the question comes up, well, this is great stuff. Why doesn't everyone use it? Well, it does cost a little bit more than most other disinfection technologies that are out there. And so what really drives this is the regulatory. Typically, people have to do it. You can't transport it, and it requires on-site generation equipment. Generation of some chlorate byproducts. These are regulated, but they're fairly low, and it does require some service in regards to the equipment. Again, we're dealing with pretty highly oxidative equipment, technology or chemistry. By nature, the materials of construction palette gets very limited, and they are very aggressive on materials itself. So they require a little bit of work. One thing I would state, another driver that has come up very recently in regards to chlorine dioxide, in particular with chlorine gas, is that we're seeing a considerable move within the industry to move away from chlorine ton cylinders. In particular, since 9/11, they don't like to have these large chlorine gas cylinders around, and so chlorine dioxide is also being considered, from a safety perspective as well, as an alternative just to deal with some of those safety concerns, both for the workers themselves and as well as the community. Just an overview. These are kind of an example of some of the generators that we provide. I won't go into the detail. I know, although most of you guys are engineers, so you get an appreciation of what this technology is. But I mean, basically, what we provide are these small little reactors. We take in 2 or 3 chemicals. We bring them in through a eductor, which essentially is vacuum feeding the precursors. It reacts, and then we're measuring pH and we're controlling. We do a full complement. We can do total manual, similar to what's over here on the right. This would be kind of a manual system where we can get into something that's much more complex, where it's PLC controlled monitoring and the whole 9 yards. But this is strictly 100% unit ops all the way, designing pumps, valves, CVs, all the things that you're learning right now. All this comes into play. I know most of you are not electrical, maybe some of you are electrical. I mean, there's some PLC stuff, but as far as the generators themselves, that we do, it's pretty much nice, simple chemical engineering design work. And just a little promotion on the technology. One of the things that separates us from our competition is that most of our competition use pumps to generate or to transfer the chemistry. We use a vacuum. So essentially what happens if there's any leaks or anything like that, we're just bringing in air, and that there's very minimal spill of acid or chloride or what have you into the environment, or even into the plant itself. So it's a very kind of a simple technology. If I can work my, there we go. Basically, we just have a mode of water that comes in through the Venturi principle. I'm sure you all remember that. We essentially got about a 40 psi pressure drop that occurs across that inductor that induces a vacuum, and we essentially regulate these precursors in to form our required concentration of chlorine dioxide that we need, depending on the application. Typically, a water plant is going to be dosing anywhere from about half a part, maybe to a part and a half of chlorine dioxide. Some more oxidative chemistries, applications, you may go up to about 5 parts per million, but that's usually about the maximum dosage that you're going after. We have capacities basically ranging from about 8,000 to 10,000 pounds per day. Just to kind of give you a sense, what does that really mean? A majority of what we produce is about 150 to 300 pounds per day of chlorine dioxide. And that basically serves a plant that does about maybe 10 million gallons per day of chlorine dioxide. That'd be like the city of Newport or something like that. When you start getting into these larger 2,000, 3,000, now you're talking like the city of Phoenix, LA. LA, you're probably looking at more like 5,000, 10,000 pound per day type of generators. a lot of chemistry going through that. So kind of just a general overview in regards to chlorine dioxide and its applications. Are there any questions, comments? Yes?
I'm not a chemical engineer, so you'll have to bear with me, but what happens to any excess chlorine dioxide that you put into some system, right? In terms of it breaking down.
So,
and then eventually, what I'm kind of getting at is, over the years, if you continue to use this process, these really low doses that you say aren't dangerous, if you keep repeating the process over and over, eventually starts to build up?
yeah, so that's a good question. It's actually, again, in regards to DuPont, one of the things that we do a very strict products, we call it product stewardship. And basically what we do is every product that we put out there, we look at it from cradle to grave. So in the case of what happens with the reaction of chlorite and chlorine dioxide, so if you remember in the previous slide, when the chlorine dioxide reacts, it forms chlorite. It can further react again if there's an acid around. It can form chlorine dioxide and go back to chlorite, but eventually where it ends up as, in the end, is it ends up as salt. It ends up as chloride in the end. So the actual end product which you're in with in the environment is essentially salt. And so that is our final end product. Again, one of the advantages in regards to, is, for example, like in the ethanol, I think this is where your question is somewhat based on. In the distillation of ethanol from corns and these grains, so what they'll do is once they've extracted all the starch and where all the and the sugars from the corn, they have all these distillate grains that are left over. Well, these go to the cows, but in order to prevent and to keep those processes operating at the efficiencies they typically have to put in antibiotics to maintain the residuals, or to maintain the microbiology activity to a point where they're not essentially souring their fermentation. But those antibiotics work their way through the whole food stream itself, and they become, and they stay with it, and you can track them throughout the whole, even into the wastewater. And just we're actually looking at some catalyst type of technology that's actually looking at dealing with some pharmaceutical drugs. I'm sure you've heard in the news right now, even in wastewater, they're starting to see, drugs that are used, for heart medication and various other Lipitor, or I don't need to name any specific brands, but for cholesterol. I mean, and they're starting to find these trace amounts of these drugs that are in the waste stream as well. And so eventually the thought is that they're going to work their way back into some of the food stuff. So we're actually looking at some technologies to help, sequester and or destroy those type of technologies. But the answer to your question is that there is no, as far as the chloride is concerned, there is no sustaining chemistry that occurs. It basically goes down to salt. So this is a very good question. Yes, Dr. Gray.
What would be a rough number as to the revenues generated from, say, the capital cost and maintenance of equipment versus your consumables?
Well, so in general, I guess you want to talk about the business plan. I guess the best way to describe it, and maybe to summarize it, it's kind of like the razor and razor blade model is what we have. So we have this generator that we use to produce chlorine dioxide. But effectively, that, only represents really a small portion of the cost, capital cost. But just to give you, a sense of the capital cost that's related to it, a system, just back up. So maybe a system will be over on the right here is probably, we'll go for maybe a $25,000, $40,000. When you start getting into systems that are a little bit more sophisticated, you're getting up into about $200,000, $300,000. But in the course of a lifetime, these will usually last anywhere 10. We have some that are actually 15 years old. But look at a 10-year lifetime. This is considered pretty much small dollars. Compared to an ozone technology, you're already up into about $500,000 just already for for ozone. Now, as far as the consumables are concerned, the chloride itself would probably represent maybe about on an annual basis. I'd say 5, maybe even 10 times the cost of the capital that you're putting in there, depending on what the dosage is and what the size of the plant is. So many times what happens, one of the challenges that we have is that, in particular, when you're dealing with drinking water. So when we have a hurricane that comes through, or we have a power failure, the last thing anyone wants to hear is the fact that they got bad water. And so these systems need to run basically 24/7, and the plants themselves and even the service staff that we have are very conscious and respond very quickly when there's an issue. Many times, a lot of the plants are running usually redundancy or have other disinfection byproducts to maintain it. So the cost sometimes, depending on the philosophy of the particular water plant, I'll just put it as an example, sometimes they may have two generators, one that's in redundancy, or they'll having maybe even 3 generators, one that's running full-time, one that's running to hit some capacity, and then the 3rd generator that's there for as a backup. So, yes?
It looks like peroxide is really good at killing microorganisms.
Yes.
Can you look at its effect on sort of chemical-based contaminants? Like I know PAHs and PCBs are becoming big emerging contaminants nowadays. How peroxide sort of reacts to them and what it does in the water.
Not so much those particular compounds themselves. There are other chemistries. This is much more. It's more the simple. If you look at the chemistry, it's a fairly simple, electron transfer. So it's just the microbiology. The spore. One of the issues that we have, although it's good at spores, spores are themselves somewhat difficult, and sometimes other technologies are a little bit better. In the case of water disinfection, spores aren't necessarily an issue, but when you're dealing with landfills or anything like that, where you may have some spores that are underneath material, the chlorine dioxide is a little bit more difficult to attack those type of materials. So.
Okay,
Yeah.
Go ahead.
It's sort of an off-the-subject question, but you did graduate from here. What was the most difficult course you took as an undergraduate, do you think?
The most difficult, you want the graduate level or
Undergraduate level.
Undergraduate level was probably Mass Transfer 3 with Dr. Bose. I don't know if is he still chairman of chemical engineering?
Brown.
Is that Dr. Brown is?
And that was more difficult than organic chemistry?
Organic chemistry was I struggled with that a little bit, but it was really just memorization. So I didn't do that bad in organic, actually.
Okay.
So.
Just curious.
Yeah.
okay, let's thank our speaker.
Yeah.